right. Hello everyone to this session on machine learning, AI, satellite imagery, and what's the impact on humanitarian mapping. It's nice to see so many people in here. Just to introduce what we are planning is we have presentations by 5 different people, and they will be around 10 minutes each. And afterwards, we will have around 30 minutes of discussion, and I encourage you to write down all your questions because we want to have this discussion after all the presentations, so you might need to cap up with your questions for the first presentation, so write them down. And I would say, maybe introducing who is here. So we have Paul. Paul will start and give us somehow an introduction into the topic, and he works for Handicap International and will go on with the Crowd AI Challenge. Then we have Hugo speaking. He works for Magellium and towards the recognition of map features in aerial imagery, satellite imagery, drone imagery, probably. Afterwards, Thao and Pierrick will present an ICRC and Picterra perspective and give us some insights how they collaborate towards like the goal of the session, so using AI. And finally, Matthew will give us more the, Martin put it like, voice of the field. So where can really these new technology or new methods fit into the needs that we have? And then I will try to wrap up everything and give a perspective from the missing maps side of things. And afterwards, we also want to have the discussion and discuss, what are the potentials and challenges we see, but not only us, also you. So please ask questions then. But now, let's start with Paul.
There are a couple of videos to start.
Do you think this is uninhabited land? No. Here you can find thousands of inhabitants, invisible on the maps. Satellite images are used daily by thousands of people, but large areas of the world have not been mapped recently. In emergency situations, humanitarians need precise maps of the damaged area. We need to get a clear picture of the situation in order to take the right decisions quickly. And we also need regular updates of those maps during our interventions.
And this is why Crowd AI and HI partnered up to launch the Mapping Challenge, which involves building missing maps using machine learning. Scientists from all over the world came together to help us solve this problem. During these 3 months, participants developed and tested algorithms to convert satellite images into accurate maps.
The stakes are high. How can we access high-definition recent satellite imagery while keeping costs compatible with humanitarian budgets? We need powerful platforms to turn these images into maps. We are confident that innovation will allow new partnerships for increased access to updated maps. This is a big hope for populations living in unmapped areas.
We follow with the next video, please.
Crowd AI is a project we started based on some philosophical ideas that we wanted our own research to be accessible to anyone. In this process, we created this large community of artificial intelligence researchers, experts, and enthusiasts. And now we try to connect problem owners from different domains, maybe a humanitarian organization, maybe a small academic group doing social science. We act as the translators in between, who take this problem, translate it in terms so that this community can understand, help set up evaluation metrics so that we can compare all these results. And at the end of it, we are making them open source, trying to become a large open repository of many artificial intelligence solutions for various problems. The mapping challenge also started with some initial discussions with Paul from HI, where in the beginning, again, this problem of can we look at an image and detect what is in there. So in the initial discussions, actually, we came up with a simple model which can look at satellite imagery and try to simply detect buildings and roads in it. And that initial model had results which were very promising, but we knew that this can be improved a lot more. That's when we put together the mapping challenge. In this challenge, we made large amounts of satellite imagery available, and these researchers started working on these problems, on trying to develop models which can look at these images and look at the corresponding annotations of where are the buildings and learn how basically to draw these new annotations when you are given a new image. And in the process, we had about 500 participants all over the world who came together to help us solve this problem. And at the end, we had a model which we were performing with an accuracy of about 93%. Imagine a conflict zone where in a particular city there's a conflict and then there's damages in buildings. And these buildings are being damaged beyond measures, but we still want to get a good estimate of what is the damage in this city. And how you would do that right now, you would hire a few human analysts who would have to go through the same image maybe every day, every 2 days. Now imagine if we could do that with a neural network which can detect buildings and say damaged buildings. You can run it every hour to get a very granular sense of what the damage has been. You can put it down in numbers over time, and you can do it faster and better probably than humans, even if the neural network is not as perfect as humans in detecting it.
Thank you.
Thank you. And I would like to have the presentation. Many of you are probably familiar with mapathons. Here's one that we had at the headquarters of Handicap International, drawing maps for our humanitarian clearance team in Laos. One of our colleagues from disaster reduction came with the question, a useful innovation would be to automate the interpretation of geometric shapes specific to cartography, points, lines, and polygons from aerial images. That was in December 2016. And what this meant was that we would need access to affordable, high-resolution imagery. We would need efficient and reliable algorithms to classify pixels. And we would need user-friendly platforms for end users. So we met CrowdAI in the meantime and started the mapping challenge. This was a proof of concept. They could quite rapidly let us know that it was possible to launch such a challenge, which was launched in January 2018 at the EPFL in Lausanne. Together with these organizations, and UNITAR provided the images that were used to separate the results from the participants. What you can see here is that we had over 25,000 views of this page, 575 participants, and 718 submissions on the 20th of August. Here are the 5 top participants. You can see here that from Neptune, we have average precision is over 93% and average recall above 94%. And all these results are, in fact, very promising and very good. The results were presented in Turin during this event on data science and advanced analytics. And the winners, Neptune, have published their results already on the internet, so you can find all the details and all the explanations about how they developed their algorithm. So the question is user-friendly imagery interpretation platforms. In June, we found Picterra in information from EPFL. And we looked into what they offered, and we understood that we could upload imagery from drones or satellite imagery to their platform. And we could draw the shapes that we were looking for and get results over the entire database. So the next question is access to affordable high-resolution imagery. I looked at the costs, the prices that you can find on the internet. And I looked at 50 centimeter resolution imagery. This is what we used for the mapping challenge. And the prices go from $10 per square kilometer to $19. This is for archive imagery. That means at least 90 days old imagery. And if you have a new tasking, then the prices go from $21.25 to $29 per square kilometer. Which means that in the case of Nepal, this map is 60,000 square kilometers. If you take this part, then it is 6,175 square kilometers. And that means that for the whole country, you would pay between $2 and $3 million, and for the reduced surface, you'd pay between $200,000 and $300,000. Of course, you can use drone imagery. That's a choice that can be made depending on the situation. And there are actors like We Robotics that develop flying labs. In this instance, this is in Nepal. And you have other actors that work on making data available. For instance, Radiant Earth Foundation. UNOSAT is releasing data as well. And you have new actors like Planet. You must have heard of these guys. They developed small Dove satellites, which they launched in space. And they also bought a few more satellites. And today, what they have to offer, they have 130 Dove PlanetScope, 5 Rapid Eye, and 13 SkySats. And you have the different resolutions that are mentioned there. They also do some analytics on the imagery that they produce. So previously a field for a few major players, satellite imaging has become a competitive open market. Many organizations can use the Planet Labs platform or other similar solutions to get the most up-to-date images instead of other free sources where some locations' data haven't been updated for years. Now, what are new sources of imagery in the future? You're probably familiar with CubeSats. The Dove satellites of Planet are 3 units of CubeSats. Now, on the internet, you find Rocket Lab, and they they're introducing an Electron launcher. You can pick the date at which you would like to launch your satellite. In this instance, it's the first quarter of 2020, and you see that 20% of the space has been booked. And here you see the prices depending on the type of CubeSat you want to launch, a number of units. In this case, the Doves would be 3 units, and that costs $240,000. If you compare this with the prices of the imagery that we saw before for Nepal, then you see that there is a potential space for business or new ways of thinking about getting access to imagery. Now, some of you might have participated in this event, AI for Good Global Summit. There was an interesting workshop here that was run by Stuart Russell with these participants on AI and satellite imagery. What Stuart Russell was telling us is that if you look at the future where you have 50 centimeter resolution images produced every day all over the planet, you have a huge volume of data that is being produced, which would cost 100 million disk storage, $100 million disk storage per year. But the situation you would be in is that you would be seeing the whole world at once. A global real-time database of everything. What that means is that today when you have a question, you go to Google and you enter your question and you get a response about whatever you can think of. What you might have in the future with all this imagery and analytics going on is if you ask yourself how many camels are there for sale this morning at the N'Djamena market, you'd get a response. So what was launched at that event is Project Zero. The Project Zero is to provide infrastructure platform to deliver continuous, permanent, global services based on automated analysis of satellite and data streams. So this could serve for weather, data and forecast, urban traffic state, global forest watch, or for instance, in the case of observing the implementation of nuclear weapon ban treaty. Project Zero is ongoing. You can get in touch with these people if you're interested. They would like to work with a crowd of people. And so you're welcome to have a further discussion with them. They know quite a bit about these issues, and there might be resources there as well. Thank you.
Hi everyone. I'm going to start. I'm Hugo Fournier from Magellium. I'm an engineer working for Magellium. I'm quite new in the company, but I'm going to do my best to show you what we can do in deep learning, at least. Wrong button. So yeah, as a machine learning engineer, how can we help in this case? Well, we can automatize mapping, as it was said before. Machine learning is quite different from traditional programming. In traditional programming, you start with data and a program made by experts, and which outputs a map or anything you want. While with machine learning, you start with a lot of data with the outputs, and you produce a program or a model that is hopefully able to generalize a result or a behavior, which can be useful on other data that has not been seen while training. So how does it work? Well, you need to start with manual mapping from images, like here, where you can see an image and is labeled you can see a building, roads, and the background. And the machine learning task is to detect the building, so to isolate where the building is, and produce a building footprint, which we call an image segmentation, where we can know which pixel is a building, a road, or anything. So how do we do it right now? The current approach, well, is to use deep learning, which is in itself a part of machine learning. Deep learning is, in fact, using deep neural networks. It's a method of machine learning, as I said before. Deep learning takes two steps. First, you need training steps, where you take a large data set and you train a model or a program with basically trial and error, and you try to make the model the best possible, and then you can use it in the inference step to produce the maps you need from data you have not seen, of course, in the training data set. In fact, we use a specific kind of deep neural networks, which is the convolutional neural networks. The advantage of CNN, as we call them, are that they look at the neighborhood of each pixel in an image, do various operations on them, and they are able to draw a conclusion from directly the pixels. And they produce an image segmentation, as you can see on the bottom, which can directly be used as a map or anything. And you can then use traditional programming to translate these masks or maps into coordinates or vector data, depending on your needs. Here is an example of a neural network trained by Magellium. You can see on the top part one data that was used in training. So there is the data, and the ground truth, as we call it, is the image labeled manually, with the building, the roads, the tree, the background, anything. And on the bottom part, we chose to output where the buildings are, and on obviously new data that were elsewhere. Here's just an example of what we can do. See on the left part, the image that was used in the inference. In the middle part, you get a segmentation of the image with each building overlaid. And on the right part, you get the vector data, which is not done by deep learning, but is made with other algorithm made in Magellium. The nice part with machine learning is that with deep learning is that with the same model you can learn a lot of features. Like in this case, you get buildings, roads, trees, standing water, vehicles, or anything with the same model. You only need a lot of data, usually labeled by hand. And yeah, I think the advantage of deep learning here is that with the big amount of data we get nowadays, we can expand the area that are not yet covered right now to other places that were not seen before. Yeah. Thank you.
Good morning. So I'm Thao from the International Committee of the Red Cross, and this is Pierrick, Poulenas, you've seen previously on the slide, from Picterra. So we are here to present a project we have together on some, do you hear me? On some image analysis that we have done previously. And we wanted to test the machine learning algorithm and how to improve it on what we would need. So, next slide, please. I'm sorry. Oh. No. Sorry. So we've been using satellite imagery for two main reasons. One is to support the assistance activities. For example, when we work in a crisis situation, we know that the camp grows steadily because of people coming into the camp, and we want to know how fast it grows. And we use satellite imagery to estimate the population based on on counting the tents. Or, for example, when we support the authorities to build a water network, we need to estimate the population, and then to estimate the population, we need to digitize the buildings. And for the other main activities is for protection activities to assess how how a conflict happens and the evolution of the conflict, the damages, and to corroborate allegation of destruction when we don't have access, because sometimes when the crisis is at high, we cannot access right away. Also to take a broader perspective, because when you're on the field and you're with your car or walking through damages, it's difficult to estimate how much has been damaged. And now with the different satellite constellation, there are many images taken regularly. So it's also a good way to understand the chronology of the events. So until now, how have we been doing this? So it's either crowdsourcing, I guess everybody knows, and you've seen also a slide, and one person doing the digitalization of the damages or the buildings. So why is the ICRC interested? So it's to save money on pizza and save my eyes. But no, more seriously, it's, yeah, crowdsourcing works, but it takes some time to have, for example, a whole city digitized, because sometimes you task a crowd, but depending on the interest, on the emergency, it takes some weeks, if not months, for an entire city to be digitized. And with a human being digitizing, we in the emergency, we may miss features that could be identified by machine learning algorithm. So I pass to Pierrick.
Thank you very much, Thao. Good morning, everybody. My name is Pierrick. I'm from Picterra. We are based in the Federal Institute of Technology in Lausanne, and this is how our collaboration starts with Thao and ICRC, because the EPFL launched 2 years ago a kind of R&D program promoting the collaboration between ICRC and startups like Picterra. So thank you, Benjamin, for the very nice introduction to deep learning and machine learning. Just a few words about what we try to do at Picterra and why it makes sense that we work together with Thao. At Picterra, we do not want to automatize the analysis of satellite or aerial imagery, but we want to put the human in the loop. So we try, basically, to first create a system, an agile system that will learn based on their expertise, based on the, let's say, I would even say the feeling of Thao, without having the need of thousands and thousands of training data. So just for you to understand what we are doing, we work on what we call interactive learning and low-shot learning. So the question is, how can you train a deep learning model with a small amount of data using human expertise? And so that's a bit the challenge we are working on with Thao. How can we, let's say, improve the analysis of images without having the need of thousands of training data and the use of these challenges? So I will go through. So yeah, Thao asked us to work on two topics. The first one was to detect the building, and the other one was to detect the damaged building. So that's basically that's the result we have over Bunya. It's the building footprint detection. So from above, it looks kind of okay. It doesn't look that bad. But when we get closer, you will see that this model kind of miss some of buildings. The reason is that the model is the one that has been used by the CrowdAI challenge, and this model has been trained globally. So it can either detect a building in Las Vegas, or in our case, kind of detect other types of building in Africa. This model it's a let's say it's an object detection model. It could be very powerful, but it needs a lot of training data to be efficient. And sorry, Thao, I forgot to mention the purpose of this project we have together is to see how much we need of Thao annotation to improve this model. And that's really what we are working on. So basically, that's the model, that's the result of the model that we ran. We say, well, it's not that bad, but not very accurate. How can we improve this model? Yeah, that's let's say a technical detail. But the fundamental question is to see how, again, is to see how many human interpretation we need to improve this huge model. This model, again, needs a lot of training data, and of course, need a lot of time to be trained. But Thao doesn't have time, actually, in your work or whatever. The second topic we have been working on is to detect the damaged building. So we use what we call an unsupervised approach. Basically, the model, it doesn't know what it has to look for in a picture. It will basically take 248 features, to be exact, and then it will compare the change of inside the pixel, if you prefer. So that's a way to visualize the change. Red, the red point is there is a high probability of change, and the white, there is no change at all. So you can see that it's not working that bad, but it can be, of course, improved a lot when you basically teach the model what it has to detect. But to go from unsupervised to supervised learning, you need to basically tell the model what it has to look for. And in that picture, you can see that there is a lot of change happening, not only on the buildings, but you can see that the road has disappeared, some fields have disappeared as well, and so on. And the question remained the same: how much human intervention is required to make this model actionable for Thao in his in her daily work. That's more or less another way to visualize the building. So we're gonna first look for the building on themselves. So it's not here. It's not the same model as we used as I showed you previously. It's a smaller model that will basically do some segmentation. It's a smaller model that needs less training data and then less time to train. I'm not doing some publicity, but on our platform you can train a model based on this segmentation approach, and with less than 100 annotation, the model will take 5 minutes to train and to learn. But the accuracy, of course, is less good than for the biggest model that I show you at the beginning. And then it's a classical change detection approach, but it's another way to visualize the detection. And that's it. Thank you very much for your attention. And I leave the floor to Mathieu.
Good morning, everyone. Wait for the slides to come up. My name's Matthew. I work with the REACH initiative based in Geneva. And I'm going to give you a brief overview of some of the things we do with satellite imagery, why we analyze the way we do, and a couple interesting initiatives that we see going forward. So in terms of our current remote sensing activities, we do a number of things, but I think we can break down most of it into two main work streams. Damage analysis is a core activity, and we do this in both natural disaster and complex emergency settings. This is an example of hurricane damage analysis in Haiti and conflict-related damage analysis in Yemen. And an even bigger work stream is what we do in shelter and settlement analysis. Out of camps, for example, we work in informal settlements, IDP and refugee shelter identification, and monitoring settlement changes. This is an example of informal settlement monitoring in Afghanistan, IDP settlement monitoring in Syria, and I think the title is hard to reach areas in Nigeria. And you can see on the left in 2013 an intact settlement, and 5 years later the settlement is gone. And this is key information for areas that are inaccessible for us. And in camp settings where we work in a number of countries, the key is shelter and infrastructure. And I only have one example here. This may look familiar to some of you. This is the mega camp in Kutupalong in Bangladesh, and colleagues digitized over 70,000 shelters in the early phases of the crisis. So this is just a small part of what we do with satellite imagery. But in terms of what we need for the analysis, we need it to be accurate and precise. We need it to be timely, and we need it to be complete. And because of this, most of what we do is manual at this stage. So manual detection, manual classification, which is lots of man-hours. In the past, we've tried automated approaches, but they always come up short. The classic problem is that historically, you may reach about 75% accuracy. And this means that you have to do the manual QA/QC process after that, and then the manual gap filling, which in total is more time than it would take to do the entire process from scratch manually. Also in the past, we've approached some very large, well-known firms who marketed AI-derived products. And our experience with this is that the marketing has been historically ahead of the technology, that they would promise a lot but not be able to deliver. But this is changing. And Paul's slide, you saw the percentages above 90%, which is a huge, huge change. So we're kind of in the gold rush phase. And our colleagues at Unisat, which Paul had showed in his presentation, have been actively involved in AI for Good and have developed a number of collaborations as a result. There are two that I've been tracking closely that I think are quite promising. UNICEF Innovation have taken a slightly different approach. The holy grail is the accurate building footprint. They've decided to not focus on this at all, and to look at using medium resolution imagery, about 3 to 10 meter accuracy, which is much cheaper to free, and the file sizes are much smaller, so you can process larger areas, with the aim of focusing on identifying settlements themselves and settlement level changes, with the ideal output being a settlement extent polygon. Unfortunately, I don't have a status update on this one for you. But another one that does focus on shelter identification and using very high resolution imagery is being worked on by Global Pulse and Unisat colleagues. And the aim here is the shelter polygon output. And I think what's a somewhat novel approach, but it's similar to what was described by the other panelists, is that taking the archive imagery and the training data and ground truth analysis that's been shared, there's a base model that's produced. And you can introduce a new image to the base model, and then you can get your fully automated detection. But what they've been working on is how to maintain the human component. So you keep a human analyst involved, and you annotate the results of the base model. So at each round, you create an adapted model that's context-specific. Not just country or region, but in the case of camps, you're making a camp-specific model over and over again. And you can keep re-annotating. So every time you annotate, you're making another model, another augmented detection. So if you can envision doing 10% manually, you can let the model run and complete the rest of the camp. If it's not accurate enough, you keep adapting the model by doing some manual digitization. They published a paper recently, Global Pulse and Unisat colleagues. I'll just keep this up there for a minute so you can take note of it. It was just published in August, but I think it's worth a view. And what they're working on based on their initial research, not sure if you can read that well, is a web-based platform that uses a cloud computing environment to support this process. So this is an image, a tile from Zatri refugee camp, if you're familiar. So you upload the image that you want to analyze. It creates a grid over it, and the analysis is broken down through the grid cells. If you look at the cells that are highlighted green, those have been digitized manually to adapt the model. And then the orange cells were done in adaptation 2 and adaptation 3 to further refine the model. So I think what's interesting here is that it's sort of shooting for a near-term solution, because I think eventually you're going to have very successful, highly automated approaches. But what this does is allow you to cut the time of the analyst down massively. So whereas it may have taken several days to complete manual digitization, maybe you can cut that time in half or make it a third, which is a huge time saving. And that's why we're quite keen on it at the moment. I'll leave it there for now. Thanks.
Okay. Hello everyone again. So thanks for the speakers already. I will go more on the crowdsourcing side of things now. We've seen in most of the presentations that some sort of training data was generated by people at Mapathons. That's what we are doing also a lot in the Missing Maps initiative. And I will focus on how we can introduce AI, machine learning into our existing crowdsourcing workflows. I'm Benjamin from Heidelberg University, and we are also working on crowdsourcing, but machine learning as well. So we try to sketch what a smarter crowdsourcing approach could look like. So basically what we have is our normal approach with some automation introduced. So we've seen it by all speakers already that satellite imagery is really crucial. And in our Missing Maps ecosystem, we have also tools and platforms that provide data, like OpenAreaMap, where you can upload your own satellite, if you have your own satellite imagery, but your own drone imagery or other kind of imagery that can be used for the mapping again. We have tools like MapSwipe, that's like a digitizing or simple classification of satellite imagery done by volunteers. We have tools like the Tasking Manager that helps organizations to coordinate mapping efforts together with volunteers. And we have also tools for mapping directly in the field, like OpenMapKit, that are all already used by most of the organizations. And now the big question is how we can introduce AI, machine learning into these existing workflow. And what we came up with is something, okay, what we would like to see is like an iteration of helping the people who are mapping by doing either information extraction or some kind of quality assessment, so validation. And in the end, what we came up with is that still people, humans, are essential in this workflow, and I think that was also clear in the previous presentations that human involvement is still required. We don't know how much, that's what everyone is more or less working on and try to minimize, but we can still conclude that we don't want to automatize everything and people will just be left aside. I think maybe if we increase machine learning and AI, we also increase the need for more people to become active in our crowdsourcing campaigns. And that's why we started thinking about, okay, we use the term AI, so artificial intelligence, but actually what we want is more like an intelligent assistance for people who do the mapping. This could be an analyst, but could also be a volunteered mapper who's doing some digitizing of building. So we think it's cool to shift that focus a bit more into that direction, thinking, okay, doing everything automatically is really the most perfection, let's say, what we would like to reach. but we would like to go with good enough and try to go with intelligent assistant first. And now I want to show you two examples. One is we have this MapSwipe app, and now we think, okay, how can we build something like MapSwipe 2.0 that helps us with all the machine learning data sets we are getting? So what are the targets? We want to improve the data quality. That means getting more completeness, but also being more precise. We want to be faster or map larger areas. And at the same time, we see, okay, what's the potential for machine learning on this? We could do some pre-processing, so filter out areas where no mapping is needed. There could be water bodies, but also cloudy areas where we don't see any building. We could do what we've already seen, some sort of building detection or settlement detection. But we could also do something that's not related to satellite imagery at all, doing some data quality analysis based on the contributions we get by the people. And then we came up with a long workflow. Maybe I don't have to go into detail too much, but just for the main phases, we have automated building detection. That's what people are working on, and we think that they will improve more and more, and then we want to rely on the algorithms. We somehow need to detect the building footprints and make them look nice. So some pre or post-processing is most of the times needed. And then this validation step could be again done by people using an app like MapSwipe. And finally, that's what we really target at, is like getting the data into OpenStreetMap, because what we've seen currently is like many data sets that are going to be produced by machine learning end up somewhere. They might be open, but end up as a shapefile or in some database. But usually it's really hard to get them into OpenStreetMap. But so far we have seen that having data in OpenStreetMap is one of the most sustainable places where data can be, because many different actors can contribute and use data at the same time. And we want the system to be still alive, even if AI and machine learning get bigger and bigger. A second example is for the hot tasking manager. So it's a tool that we use to coordinate mapping, and there have been a lot of discussion how AI could improve the tasking manager, so how could we better allocate tasks to volunteers. And the first things that we came up with is maybe not the perfect building footprint estimation, but maybe simpler tasks like prioritize mapping areas. So if it's enough to estimate the number of features in specific places, we can better estimate how many mappers are needed to completely map this, or split up our area in different sizes, that you don't end up with one task where you have to map 1,000 buildings and the other only 10 buildings. So it's not the holy grail of getting the building footprint, but some easier targets that would still help us a lot doing the crowdsourcing process. And of course, we had this validation aspect already again, so we could then also compare between what has been estimated by the machine and what has been actually mapped by the volunteer, and try to use that as a proxy for how complete has the mapping been done by the volunteer. Tell me where I've missed something, or for the next step, also detect the areas with the most quality issues, that we can tackle them with more experienced volunteers, or try to address it in our workflow, or give better training to the people. And there's already some sort of better version for this built by Development Seed, where they put some machine learning predictions into the task manager, and just in the direction that I've told you, just estimating here they call it difficulty. Difficulty means like how much needs to be mapped in this sense here. So that's really a basic model applied, but in the context of humanitarian mapping, and what now needs to be assessed, is this really helping us in mapping this area? So this is still not so clear, I would say. And now I would say I want to wrap up with some challenges, and maybe that's also the point where every one of you now can start thinking, because after that we will directly go into the discussion round, and I will like to collect your questions. But first, I divide it into technical and non-technical challenges. So from the technical side of things, it's more like we need to really ensure that the tools and the data sets that are used and created are open and accessible, because that's what we have seen also in the past, that if tools become open, it's much more powerful than if we have just solutions targeted to one specific organization for one specific need. We still need a better understanding of the quality of the AI data sets, and we also need to communicate them. So we've seen this today already, so we somehow communicate them with our model has an accuracy of 93%, but what's the impact or the meaning of these 93% is often not so easy to understand, so that's also a bit technical challenge, but we need to provide something there. The third point that I already mentioned is that integrate the data into the OSM database and the processes is something that not so many people are working on at the moment, so it's good that we have a lot of people working on the first part, how to get AI data, but the integration part is not so much happening. Fourth point, I think that's already maybe where we've seen already a lot of progress and presentations today, like build the infrastructure to do it. So all the speakers have highlighted there's a potential to save a lot of time if we can do it automatically, but only if we have the infrastructure set up and really can spin up our model within, I don't know, minutes, hours. What's our target here? So that's also something we need to keep in mind, that there's something behind those models, that infrastructure that needs to be there to get things out of it. And that might be a technical challenge for some organizations. Okay, now the non-technical part. So if we increase like data flowing in from some machines, we also might increase the need for experienced mappers or analysts to validate what has been produced. So can we keep up with the scale of the models to validate what has been produced? We're never going to validate everything again, but still validating only small fractions or samples will also take time, and we need to account for that. What can we actually map, or what can actually be mapped automatically? And while we're focusing on AI and machine learning, are we forgetting something else? Maybe the more local perspective, mapping in the field using GPS devices or smartphones. So this discussion here should not like make us forgetting that there's also some local mapping that needs support. There's also increased technical know-how for project managers who want to use those data sets. So they need to understand the results. They need to understand how they can introduce it into their own workflows. And finally, just potential source of new bias. I think it could be a longer discussion, but thinking about what has been detected in the model, what has not been detected. If we talk about buildings, what kind of buildings are easier to detect and what kinds of buildings are more likely to be missed. There's also some sort of new question we need to ask also in this context. We already asked those questions in the crowdsourcing context, so we think about what are the mappers good at and what are they not so good at. We need to ask the same questions also for the machine. Okay, but now let's try to open up the discussion for everyone. Thanks all speakers again, and I'm curious to hear now from our audience. Thank you.
Hello, my name is Gilles Morin. I'm a CTO of a private company called Masai Analytics. My question is about combining remote sensing or satellite imagery we've seen here with some ground level imagery like you can find on Mapillary. Are there any AI workflows that you're currently aware of that combine the two?
Can we add up some questions to that?
Yeah, please go.
I had 3 quick questions. Has someone thought about using the previous mapathon exercises as a training data for machine learning? Second question is, we've seen a lot that we can do a lot of things with very high resolution imagery, but what is free now is medium resolution imagery, and Sentinel is 10 meters 10 meters resolution. What can we do about that? There has been a lot of move in terms of land cover classification all around the world. Can we put that into for use for humanitarian or for OSM? And in particular, I've not heard about radar data. I think there is Sentinel-1 with radar data. There is also high resolution radar data. What can we do with that? Can we not have something useful with that? And the last question goes with this one, which has to do with crossing with other sources. Have you worked into using other data? In AFD, we are supporting the opening of cell phone data with building APIs in Senegal, Colombia, and Philippines, where public good actors or National Statistical Institute can send queries to the database of the cell phone operators to get data that can be analyzed with the location data that they have from their customers. But this is one very specific example. Are there other examples of other sources of data you might use to enrich your classifications?
Okay, just to repeat maybe. So we had the first question with AI, mapillary, street level images, and then OSM data from mapathons using as training data sets. Resolution regarding land cover, what can we do with it? Radar data and other data sources. I will go maybe for the first 2, and then I would like to give over to someone of you maybe. But for using street level images, so I know that companies like Mapbox are doing things into that direction, where they try to detect, like, most of the time features that are related to the street network, like traffic lights or traffic signs or something like this. There's so far, at least as I know, not so much regarding street level images in the humanitarian mapping world. Maybe everyone else can correct me, but I suspect that because of the limited availability of street level images in most of the countries where we would like to have the maps that are missing. So there's something, but more or less in the US, European world. Regarding the using OSM data that was created during mapathons as training data set, I think everyone is already doing it, I would expect. So that's basically OSM is one of the biggest training data sources that is being used for these kind of models we've seen. So that's already happening. Yeah, someone likes to comment on resolution, radar data, or other data sources.
Yes, about the question about using, I mean, the relationship between high and low resolution is something, I mean, fundamental in our world, and especially, and I guess in your world, because there is always this question of cost. There is something which is coming. It's called transfer learning. And the idea basically is to train your model on very high resolution, so let's say 1 meter resolution, and then to transfer the learning to a lower resolution. And I think that will that's really a key challenge for on your side, but also on our side, if we want to make AI and imagery accessible. In terms of cost, but not only. So imagine that you can train. So you buy your Planet or your Airbus satellite scene, and then you train your model, and you can transfer this the model on Sentinel-2, for instance. And you just need to buy a very high resolution every 3 months to check that the model has not deviated too much. But it's still really R&D level, because in that situation you need to go at the sub-pixel resolution to train your model. And about the usage also of external data, Benjamin, you will confirm that. For instance, there is a model, the ResNet, which is used to do segmentation, has been trained on cat pictures. So we use this model to detect a building on satellite imagery, but at the beginning, he has been trained on cat picture. So just to say that deep learning can accept a lot of different data, and the more diverse the data are, the better the outputs will be, if I summarize.
Someone experienced with radar data? I'm not so experienced, but
I recently had a short training on radar sentinel data, and what I realized with my colleague is that the learning curve is really steep because it's a profession. You just don't improvise like because it's similar to optical imagery. So there is the technology is here, I think, and the thing is to push it's complementary to optical images because it can analyze certain issues that optical imagery cannot, and vice versa. And for the time being, the radar images are 20 meters on Sentinel, to my knowledge. But I know that some microsatellite will be launched soon. So this might also change the game. And until now, what I've seen is that people who can analyze radar imagery are mostly academics, but they are willing to help as well. So maybe this is something we could explore more.
okay, more questions, please.
It's more going on the subject of radar imagery. Actually, we've done, and I'm not an academic, we've done analysis on Mosul destruction when the city was taken back last year using Sentinel-1 radar imagery. So to have a very wide assessment of the destruction of the parts of the city, we use Sentinel-1, which is, as you said, lower resolution than what is used usually, but can provide the bigger picture in the whole urban area of Mosul. And we've done that in Sana'a too recently.
Hi, I'm Gaurav Thapa from Kathmandu Living Labs. So my question is slightly different. It's more on the lines of, I guess, non-technical aspect of things that you showed over there. So with AI and imagery recognition being improved and more, our ability to draw, trace buildings and roads improving drastically, one thing that I've noticed in the OSM community and also in generally is that people are slightly hesitant about this replacing human mappers, and the hesitation has more to do with tracing of buildings and roads is some of the simplest task, and that's what like beginner mappers tend to do. So when you're trying to first introduce mappers to OpenStreetMap and bring them on board the community, one of the driving motivation for them is to be able to map remotely in various parts of the world for humanitarian needs and feel part of the humanitarian effort that goes into relief work and later on all sorts of other things. But like that initial motivation that they're contributing to a humanitarian crisis or effort, is there a line where we can, or is there a thought where the AI portion should be more about the complex things such as maybe radar interpretation, more like, where experts are needed, but the simpler tasks should be still more about just normal people doing it, like tracing buildings and roads?
Okay, yeah, thanks for that question. I think that points to a really important discussion within OSM and how OSM volunteers or people like will interact with machine learning. So I think it's really difficult discussion to say we will leave the easy tasks for volunteers only, even if we could do it automatically with a really high precision. I think there's maybe also no meaning in asking people to do things that are not so valuable anymore. But I see the point as well that that's how we introduce people to OpenStreetMap. So we tell them, please map a building, please map a road, and while doing it, you become more experienced, and then also start to map other things, start to map in your local neighborhood, and so on. So that's maybe the huge impact that we see now, and still don't know how to handle it. How can we introduce beginners to OpenStreetMap if not so many buildings need to be mapped anymore? And do we need different ways of mobilizing people and also telling them what their impact is? If you say, I think Martin put that already on a hot mailing list some time ago, it's like, is it okay to tell people you contributed to a humanitarian crisis by validating this automatically generated building footprint? Is this still satisfying to you, or is it just, I just did a click, you know, but maybe, I think for the next years at least, I would say, there's a need for both. We will still need many people who will do digitizing of buildings and footprints and streets and so on. Because what we've seen for most of the models is like the importance of the training data sets, and if training data for the specific region is not available, most of the models will also have problems. So at least to create training data, I think we will still need many of those beginners, and that's still a valuable contribution.
Hi, Benjamin with Mapbox. Oh, sorry, excuse me.
If I can add something, is the microphone working? Okay, yeah, okay. What I can add to this is that you also have a community of machine learning students who are very active in learning their skill. You have seen that in our mapping challenge, you had more than 570 participants. So there's a community out there as well. What we need to keep in mind is that the volume of data that needs to be handled in the future is going to increase tremendously, and that human eyes just cannot follow that pace. And that within a few years, we will absolutely need to have the tools that are of the quality that we need to do the analysis of what will be expected. That means that when you have an emergency situation, you may want to analyze a new map every day, for instance. And that's a huge amount of data to be analyzed. And so we need to integrate what human beings can bring. But we also need to integrate what young researchers are developing, and keeping pace with the volume of data that is being produced and that can be used correctly.
I will just add something on that. Of course, I have a different point of view because we are working on this low shot learning system, and I don't believe in the future we'll need this army of annotators working on creating training data. We can also rely on a machine to create this training data. Just to give you an example, if you annotate an object, the machine can create out of this single example, can create 10 annotation data. But by rotating the image, changing the color, the contrast, and it's a bit Inception stuff when the machine creates itself the training data to train itself. But let's say that in the future we, okay, the community you're talking about, this machine learning engineer, this open challenge, these are very good, but in the future I don't believe they will be there anymore, because this amount of training data is clearly reducing. Again, I come back with this example. So if we take a small model, the model that has been trained on cat picture, the model is a tiny one, so it's not super accurate, but still. So we come back to the debate of this morning, good enough versus perfection. With the ResNet model that has been trained on cats, you can do already a lot of work in detecting building with a small amount of annotation, less than 100. And this is only the beginning of this train. So in the future, you will need probably tens of training data to train a small model and to get immediate result after 10 minutes of training. But then it doesn't mean that we won't need anymore the human, because I see this more as something iterative. You give few examples, you get immediate result, you launch, you check, then you can share also this work. So the future will not be on creating this training data, but more on building, on improving this tiny model to make them more accurate.
So Benjamin with Mapbox. The question I had was about the conflation problem. So as we'll have more and more AI-generated data, we'll need a better way to merge it with existing hand-mapped OSM data. How do we decide when to update features, when existing features should be kept, etc.?
Yeah, I think that's exactly the right question that we are currently also trying to get closer to the answer. What we try to do now is like setting up or adapting our crowdsourcing system to allow volunteers to decide on their own, to say, is that a change or is that not a change? And of course, you can also think about some automated analysis. Like, it's easy to get if this place has already mapped or not in OpenStreetMap. That's not a big problem there. But really decide whether something has changed or not. At least my feeling is, we can discuss that, is that still something that the humans are deciding in the end. And we've seen it in many presentations. It's like you need to define thresholds and all this kind of thing. That's quite a human kind of thing to do, but please comment on this.
Yeah, and you mentioned this earlier about the possibility of hacking a deep learning model. It's about this feature. I don't know if you remember the slide when I showed the first detection based on mask RCNN. Some buildings are perfectly detected, and the same building just next to it is not. So it's among this feature. No, there is a variation that happened inside the model, and we don't know which variation has caused the deviation of the model. So that's something that we have to live with, and that will still be there, I think, in the future. And so I changed a bit. I opened the debate, but all about these autonomous vehicles and so on, they can be easily hackable. Can we say that? Hacked. Sorry. Because if you change a small feature in the model, this can completely change the output. So human will still be there in the future.
That's very reassuring. Luke Cayley from the IFRC. I think we've only got time for one last question, so maybe really short, but thanks a lot for your presentations, by the way. In terms of these techniques, not just on its use for automated classification, the deep learning and artificial intelligence, in terms of its potential use for supporting humanitarian decision-making. So potentially, you could look at pre- and post-event imagery, linking this to needs assessment data, and learning based on that what the kind of figures might be for estimated population. This is one area that people are looking into. What other areas do you think there might be kind of potential for us to explore with the technologies and the imagery that we're likely to have in the coming years? Thank you. So a bit more blue sky.
The first thought that comes to mind, I mean, we've talked about a lot of sort of static situations, people in a certain area. But some of the presentations talked about the new constellations of satellites going up. There's going to be more and more, and pretty soon there'll be daily global coverage. And I think we're going to see an advancement in tracking displacement on a daily basis in the near future. As soon as this imagery becomes available and some of the medium resolution models improve, I think we'll get very good proxies for locations of displaced populations along the route.
And on my side, I see, let's say, a very good opportunity with the development of this technology, a good opportunity for community, for let's say the civil society in general to while accessing this imagery plus artificial intelligence. There is a lot of opportunity for the people I mentioned to be empowered by this technology, and to now we are living in a world of information and transparency. If how can I say that? A group of operation or lobbyists or NGOs and so on have access to this. And with the daily, even several times per day, if you have this imagery coming and the power of analysis coming with the AI, imagine the power or influence that you will have on people polluting the oceans or polluting the lands, or saying that no, there is no mine here. We didn't cut this. We didn't cut trees in the Amazonia. Imagine the transparency that this technology will bring to the civil society, and I don't know what we could do with that.
With the pitfall that we might identify people who don't want to be seen. For example, displaced people who want to hide from any party, and then we know where they are. What shall we do? I don't have the answer.
I don't have the answer either to that question, but maybe one last thing is, like, I think you're right pointing out that most of the things that we presented here are based on using satellite imagery and machine learning, but of course we could also use many other kind of data sources without satellite imagery, and that might be too broad for this discussion here, but this will also have a big impact on decision making.
So I'm afraid we're running out of time. We have to stop the discussion here. Benny, you don't mind if I say a little word of conclusion? Because I prepared the panel with them. So I'm Martin from CartONG. I think we can all agree after this panel that I suppose this evolution towards AI will happen, and the debate is more like on the rhythm and the specifics, and we have our technology enthusiasts saying it's already there, or skeptics saying maybe in a few years. To me, the question is really like what was discussed by the panelists of how can we make sure that we will still need human, whether it's for like assessment, like Matthew said, or for instance, if you want to merge data and create a new data model in OpenStreetMap and you have to go to the OpenStreetMap working group, data working group, a machine will never do that, for instance, negotiate with humans on the evolution of the platform. So we will still need these advanced people having skills. And I think it would be a waste if we lose all this interesting ecosystem we have, whether on the OSM side or more generally, all the people that work in manual analysis. So how can we smoothen this transition so that we add some machine learning more and more in our processes without losing our volunteers or our contributors, etc. So I count on the panel and all of you to discuss about that during the break and the lunch that is now coming. Thank you.